So, welcome back to this lecture series on pulse width modulation for power electronic converters. So, after a fairly long discussion on varied kinds of power electronic converters such as DC-DC converters and DC-AC converters, multi-level converters, etc., we have started working on pulse width modulation now. We are focusing on a 3-phase voltage source inverter, and we are trying to do some pulse width modulation assuming very few switching cycles within a fundamental cycle now. So, let us look at a 3-phase inverter. So, what we are doing is basically a low switching frequency PWM, that is we are trying to modulate the inverter such a way that the switching frequency is very low. So, as I mentioned earlier, this helps us understand the idea, the concepts behind pulse width modulation better when we deal with low switching frequency, when we deal with very few switching cycles within a fundamental cycle. Also, this is relevant for high power drives. So, where the power levels are so high that the energy loss per switching transition is so high that you can't do too many switching transitions, have too many switching transitions in a cycle. Yes. So, let us just take a relook at a voltage source inverter. So, voltage source inverter has DC on one side and 3-phase AC on the other. So, these are the load terminals as we know, and these are the DC terminals we know, and these are going to be modulated. What do we mean by modulating? The R phase or any of the poles could be connected either to the top throw or to the bottom throw. When to change over from top to bottom, this is what we are trying to do in pulse width modulation. Instead of looking at it as generic switches, if you look at it at actual with actual transistors and diodes, this is how the circuit looks like. So, every leg has basically 2 transistors with anti-parallel diodes, and these conduct in both the directions and they block voltage in just one of the directions, as we have seen a number of times before. So, this is like a single pole double throw switch, because if the top is on, the bottom will be off, vice versa. So, R will be either connected to the positive DC bus or will be connected to the negative DC bus. So, this is a single pole double throw switch, as we have seen. So, this purpose of pulse width modulation is what we want to do is we will have the DC voltage being fixed or maybe unregulated, regulated or unregulated, whatever. So, it does not vary by itself. So, I mean it cannot be controlled. We want to control the AC side fundamental voltage. The question is how to do that. So, the pulse width modulation should help us achieve the desired amount of fundamental voltage now. That is something that pulse width modulation should help us now. Apart from controlling the fundamental voltage, there are several other harmonic voltages which we do not want them, we might not want them, but then still they exist. So, what we try doing is we cannot totally avoid them, but we try to reduce or mitigate those harmonic voltages or mitigate their harmful side effects. So, these are the 2 main purposes of pulse width modulation, as we have seen earlier. So, what we have been doing is, first if you look at a square wave, or you can look at just one switching angle per quarter cycle, you can control with square wave, you cannot control the fundamental voltage. With one switching angle per quarter, you can just control the fundamental voltage and you cannot influence the harmonics. So, now we have been looking at 2 switching angles. So, what we are looking at here is the pole voltage VRO. R is the load terminal, R is this is R and O is this. So, here what we are looking at is the voltage at the midpoint of a leg measured with respect to the DC bus midpoint. So, it is 0.5 V or minus 0.5 V, where V stands for the DC bus voltage now. So, you have 2 switchings per quarter, that is alpha 1 and alpha 2. So, the waveform has all the symmetries, and therefore, we are representing only one quarter. In case you wish to know how it will look in the other quarters, what you can do is about this 90 degree, you just reflect this waveform. You reflect this waveform about 90 degrees. So, you will have something like this. So, this is at 180 degrees and this is 180 minus alpha 1 and this is 180 minus alpha 2. So, you will have something, you reflect this, you can get the other quarter, and using half wave symmetry you can get the second half now. So, that is how the actual full waveform is. We look at just one quarter because that is sufficient for us. The switching angles in the different quarters are related to one another. So, these are the only 2 independent control variables, alpha 1 and alpha 2, right. So, we saw that it is convenient to look at all these possible waveforms on a plane where it is alpha 2 is represented against alpha 1. Every point on this plane, you take any arbitrary point on this plane, it represents a pair of alpha 1 and alpha 2. It basically represents some waveform like this. it represents a pole voltage like this with alpha 1 and alpha 2. In this case, the alpha 1 I have chosen is roughly 15 degrees and alpha 2 is roughly 45 degrees in what I have indicated here. So, every point represents actually a waveform like this now. So, there are limits on these angles alpha 1 and alpha 2 as we saw last time. So, the constraints are 0 degree should be less than or equal to alpha 1, alpha 1 certainly cannot go below 0, and again alpha 1 is less than or equal to alpha 2. So, alpha 1 cannot exceed alpha 2 or alpha 2 cannot go below alpha 1 and alpha 2 again cannot exceed 90 degrees. So, you have this condition 0 less than or equal to alpha 1 less than or equal to alpha 2 less than or equal to 90. Now, this is the line alpha 1 is equal to 0. Now, this is the line alpha 1 is equal to alpha 2 and this is the line alpha 2 is equal to 90. This is alpha 1 is equal to 0, this is alpha 1 is equal to alpha 2 and this is alpha 2 is equal to 90 degrees as we have seen before. So, all the points that we consider are they should be within this region. So, outside this region is not acceptable. So, these are our constraints, we need to operate within this triangle, that is our constraint now. So, we look at all possible waveforms within this and try to get a waveform which gives us our desired fundamental voltage, and then we can see whether it can give a better harmonic voltage also, whether the harmonic voltage can be reduced also. So, if we desire 80% fundamental voltage, can we get 80% fundamental voltage with much reduced fifth harmonic or seventh harmonic voltages for example now. So, this is the bounds within a switching plane. Now, for example, if your desired fundamental voltage is 0, the fundamental voltage has this relationship V 1 is equal to minus 2 cos alpha 1 plus 2 cos alpha 2 equals 0. I mean this is for the 0 fundamental voltage. So, this is the equation for V 1 for based on that is how we calculate the Euler coefficient in the Fourier series. So, you have this equation. Now, if you want V 1 is equal to 0, we got several points. You can plug in several values of alpha 1 starting from 0 to 60, you get corresponding values of alpha 2 going somewhere between 60 and 90, and we got this curve indicated as V 1 is equal to 0 here. This curve we got, this is the curve we got. Along this line, you have waveforms, all of which give you a fundamental voltage of 0 amplitude. The waveform's instantaneous value is not 0. The pole voltage waveform's instantaneous value is either plus VDC by 2 or minus VDC by 2, but its fundamental amplitude is 0. That's what you mean here now. So, we have taken some examples also 0 comma 60 degree is by indicated as point A, and 60 comma 90 is the other extreme point indicated as point B, and some point C which is 36 comma 72 degrees. So, we saw that there were some good and bad examples of the 0 fundamental voltage. Now, if you take 0 comma 60 degrees, if you take 0 comma 60 degree, what happens is there is actually a switching at 0 and at alpha 1. Now, alpha 1 becomes 0. So, between alpha 1 and alpha 2 the waveform is going to be negative. So, what you get here is the waveform is going to look like this. This is 0 and this is alpha 1 which is equal to 60, this is alpha 2 which is equal to 60 degrees, and it is like this 190. If you draw this beyond this, at 120 degrees it goes low, at 180 degrees it goes high. This is the nature of the waveform you have. So, this is actually a third harmonic square wave as we saw the other day. This is a good example of a waveform with 0 fundamental voltage. Why? It is having a 0 fundamental voltage and it does not have fifth harmonic component for example, it does not have seventh harmonic component for example, it only has third harmonic components, and the third harmonic components vanish when you subtract VRO minus VYO to get your line voltage VRY. So, third harmonic component, when VRO is phase shifted by 120 degrees, all the triplet harmonics, the third harmonic, ninth harmonic etc. are all shifted by certain integral number of cycles. The third harmonic is shifted by 360 degrees at its own frequency. So, when VRO and VYO are subtracted, the resultant waveform has no third harmonic. The resultant waveform will have no ninth harmonic and 15th harmonic etc. So, VRY will be just 0 and it will not have any fifth or seventh or anything like that. Alright. The same way, if you take 60 comma 90, that would be again a third harmonic square, where it switches from low to high at 0. At 60 degree it is from high to low, then at 120 degree it goes back, and at 180 degree it comes low. So, this is also a third harmonic square. These two are in phase opposition, but that does not matter, both are equally good, because when you subtract VRO, I mean when you VYO from VRO, or one pole voltage from another pole voltage, you are not going to get any third harmonics or any harmonics going to be there now, right. Now, we also considered the other example of 36 comma 72. Here it switches at 0 degree and it down at 30 degree, goes up at 72. If it goes up at 72, 72 is 18 degrees before 90. So, 18 degrees after 90 is 108. So, it comes down at 108. If it comes down at 108, it will go back up at 144. So, basically 144 is 180 minus 36, and then it comes down at 180. So, this is one half of the waveform, and you can see that one half of this waveform is actually 2.5 cycles of a square wave at the fifth harmonic frequency. So, this waveform is also an example of a waveform whose fundamental amplitude is 0. All three are examples of the fundamental amplitude being 0. The first to have no harmonics, but if you look at the last one that I just drew, it has a lot of harmonics. It has fifth, it has 15th, it has 25th, it has 35th, and all these harmonics. So, VRO contains all these harmonics. When you subtract VRO minus VYO to obtain your VRY, VRY will also have fifth harmonic. VRY will also have 15th harmonic. 15th harmonic will go away because it is a triplen frequency, but VRY will have 25th harmonic. So, 5th, 25th, 35th, such harmonics will be present in VRY. So, though you are applying 0 fundamental voltage, you are applying certain harmonic voltages, or let us say you are applying not exactly 0, a small amount of fundamental voltage, but what you will end up applying is a large amount of fifth harmonic component, and the operation of a motor could be very bad in terms of there could be lot of pulsating torque and so on. So, this is look at the other constant fundamental curves now. So, the first line that we looked at, which is this, the blue one, this is the line V1 is equal to 0, which we just looked at, and as we go on at point 2 for example, or some such number, you for a higher fundamental voltage, you look at a constant curve, some V1 is equal to constant, you got a curve like this. You go for still higher value of V1, and for V1 is equal to constant, you get a value like this, and you go on like this now. So, there are several V1 is equal to constant curves that we plotted last class, and V1 increases in this direction as you move along, and V1 is equal to 0 along this line, and V1 is equal to 1 along this line. So, between those two lines you have any V1 is equal to constant contour will be between those two curves. Now, let us say we had a look at the slope now. So, what is the slope of this curve? It is changing. All this V1 is equal to constant contours, the constant fundamental voltage contours, their slopes keep changing. So, let us take some V1 is equal to constant. So, what is that? V1 is equal to 1 minus 2 cos alpha 1 plus 2 cos alpha 2. This is some constant, let us call it k. So, if you differentiate both sides, you end up getting something like 2 sin alpha 1 minus 2 sin alpha 2 d alpha 2 by d alpha 1 is equal to 0. Therefore, you get d alpha 2 upon d alpha 1 is equal to sin of alpha 1 by sin of alpha 2. This is the slope of constant fundamental voltage contour at any given alpha 1 and alpha 2. If it passes through some alpha 1 and alpha 2, sin of alpha 1 by sin of alpha 2 is the slope of that contour. So, whenever it cuts the vertical axis, alpha 1 is 0. So, the slope should be 0. So, if you see, the slope is actually 0. The last two curves shown here, it seems like they do not have a 0 slope, but that is basically a drawing inaccuracy, and you need to be careful about it, and I am sure you can do a better drawing than what I have done. So, it is basically, it should be something flat and going like this. So, it should be basically something flat and going like this now. Whereas, on the other end, if you look at alpha 2 is equal to 90, it is sin alpha 1 by sin alpha 2. So, sin alpha 2 is sin 90 is 1. So, the slope is simply equal to sin alpha 1, which was one of the last observations that was made in the previous lecture now, and it is more or less it is like a line with slope is equal to sin of alpha 1 at those points now. So, that is what we may have to observe about the slope of all the constant fundamental voltage contours now. So, shall we say what happens when we go beyond that, though we are not really interested. We are not interested beyond this region, but let us say if we go beyond, what will happen? This curve will go on increasing, and what will happen to the slope? At some angle sin alpha 2 can become 0. What is that angle at which sin alpha 2 can become 0? After 0 it is 180 degrees. So, at 180 degree these curves they will go on and they may become vertical. These curves will tend to become vertical, and again when you come back, when you come back it is going to be 0 when it cuts the x axis. So, let us look at that when we actually look at the constant harmonic voltage contours. What I am trying to say is these curves are in fact closed curves, they are not open curves. We are only seeing a portion of those closed curves, and this will be clear when we look at the constant fundamental voltage contours, which we are going to see in a little while from now. So, the slopes are really changing like this, and the slopes will help you plot them very easily. So, now what we need to do, let us say I want to plot all of them now. I have a good knowledge of the contours, the nature of the contours, some knowledge of them at least. So, what I need to do is, let us say I look at the contours, do some calculations. What is that? V 1 is equal to 1 minus 2 cos alpha 1 plus 2 cos alpha 2. This is in per unit term. Here 1 per unit stands for the amplitude of the square wave during, amplitude of the fundamental during square wave operation. So, it is basically 2 VDC upon pi. So, that is 1 per unit, that is the base quantity here, alright. So, 2 VDC upon pi is taken as 1 per unit. So, that is what is taken there, and the 2 VDC by pi term is hence not shown explicitly. So, if you take along alpha is equal to 1, your cos alpha 2 is simply when alpha 1 is equal to 0, this 1 minus 2 cos alpha 1 becomes totally minus 1. So, cos alpha 2 is 1 plus V 1 the whole divided by 2, 1 plus V 1 the whole divided by 2. So, here you can plug in several values of V 1 to get the corresponding values of alpha 2. So, you want V 1 is equal to 0 at alpha 1 is equal to 0. So, when V 1 is equal to 0, so you have cos alpha 2 is equal to 1 by 2, that is 0.5. Therefore, alpha 2 is equal to 60 degrees, it is fairly easy. Then if you are looking at V 1 is equal to 0.25, then your cos alpha 2 equals 1.25 by 2, that is something like 0.625, and the corresponding alpha 2 is 51.3 degrees. And if you are looking for V 1 is equal to 0.5 along alpha 1 is equal to 0, then the corresponding value of alpha 2 is 41.4. Similarly, if you are putting 0.75, if you are interested in V 1 is equal to 0.75, you are going to get alpha 2 is equal to 28.9. So, let us go back. Now, if you want V 1 is equal to 0 along alpha 1 equals 0, this is your V 1 is equal to 0. Let me call this as 0 here, write 0 here. This is V 1 is equal to 0. Then if I want 0.25 along this line, what I got was alpha 2 is equal to 51.3 degrees. So, this is something like 51 degrees, let me say. So, this is my V 1 equals 0.25. And if I want V 1 is equal to 0.5, the angle is something like 41.4 degrees. So, the angle is 41.4 or here, something like this. Again there are certain drawing inaccuracies. Anyway, this is 41.4. So, now you go to V 1 is equal to 0.75, it is a little lower than 30 degrees, that is 28.9, somewhere here is there. So, we know that these are the points for V 1 is equal to 0, 0.25, etc. So, if I want to finish that on the other side, V 1 is equal to 0, what I need to do is, let us say I can see how it passes through alpha 2 is equal to 90. It is easy for me to consider alpha 2 is equal to 90. So, V 1 is the same expression 1 minus 2 cos alpha 1 plus 2 cos alpha 2. If I consider along alpha 2 is equal to 90 degree, I have cos alpha 2 is 0. So, that makes the calculation simpler. So, cos alpha 1 is equal to 1 minus V 1 the whole divided by 2. So, if I want V 1 is equal to 0, along alpha 2 is equal to 90, alpha 1 is 60. If I want V 1 is equal to 0.25 along alpha 2 is equal to 90, alpha 1 is 68. Again for V 1 is equal to 0.5 along alpha 2 is equal to 90, it is alpha 1 is 75 degrees. So, if I look at it here on the onto here, this is my 0, this is my 0 and this is my 1, which is square wave operation there. If I want 0.5, I can roughly take the middle of this, which is around 75 degrees, alpha 1 is equal to 75. Why can I take it as, how can I take it as roughly in the middle? Along this line, what varies is just alpha 1, alpha 2 is 90 and what varies is alpha 1. What is the range over alpha 1 varies? Alpha 1 varies between 60 to 90 degrees. So, if you consider cos of alpha 1 and its variation between 60 to 90, it is fairly linear. So, if you look at cos alpha 1, this is at 0, this is at 90. So, between 60 and 90, it is fairly linear. It is a sinusoidal curve, any sinusoidal curve closer to its 0 crossing is fairly linear. So, that is what is happening now. So, if you 0.5, do not be exactly at 75 degrees, just a little farther as we got here. It is, it has been 75.5. Again, if you want V 1 is equal to 0.25, it will be quarter the distance from here to there. So, which I would say 67.5, the actual number could be 68 degrees. So, which is not too far. Similarly, for 0.75, I will have it here, which is 3/4 the distance from 0 to 1 along this line. So, I have all these points, I can actually go about joining them. The other thing that I know is the slope. What is the slope here? The slope is sin alpha 1 by sin alpha 2, just as we derived a little while back. So, along alpha 1 is equal to 0, your slope is 0 because sin alpha 1 is 0. Again, along alpha 2 is 90, you have sin alpha 2 is equal to 1, therefore, slope is just equal to sin alpha 1. So, if you go back here, I know that the slopes here are 0, I know that the slopes here are 0, the curve is flat there. And how about the slopes there? Here the slope is equal to sin 60, that is root 3 by 2, here the slope is equal to 1. So, in all these cases the slope is somewhere between root 3 by 2 and 1, that is basically equal to sin alpha 1 now. So, with these two ideas, I can roughly sketch all these curves that I want to. I am just going to sketch these curves. So, this is just for us to clear up our understanding of the constant fundamental voltage contours now. Okay. So, these curves are they are of 0 and then there is some slope here as we go on, and these are the varied kinds of curves now. So, once you have these, what we can do is, let us see what we want to mean by a PWM method. You have several of these contours. So, let me just draw one or two of them, let me just draw a few of them, something like this. So, what do we mean by PWM technique? You should be able to control the fundamental voltage. How can you control the fundamental voltage? You want a desired fundamental voltage. Let us say I want this fundamental voltage. Let me take a different colored ink. Let me say I want 0 or something very close to 0. Okay. So, let us say I want to operate here. Now, I want some other fundamental voltage. I can operate on any point on this curve. I can operate on, let me just draw a few more curves for clarity. So, let us say here. So, let us say I want a higher fundamental voltage now. So, higher fundamental voltage corresponding to the second curve that I have drawn here. I can operate basically on any point along this to get that fundamental voltage. So, let me say I operate on this point. Again I want fundamental voltage equivalent to what the third curve gives. Again I can choose any point along this third curve. Let us say I choose this red point. Similarly, for the fourth blue curve, it has some constant fundamental voltage. Let us say it is something like 0.8 or so. I want V 1 is equal to 0.8. I can operate at any point along this curve, on this curve. Let us say I choose this point now. So, basically then I want to go to say full voltage or 100% voltage or 1 per unit 2 VDC upon pi, that is basically square wave. So, I can do this now. So, what I can do is, basically what I am doing is I am moving from here all the way to here. So, this red line now represents a PWM technique. We are considering a 3 phase voltage source inverter, we are considering that it is switched with all the waveform symmetries, and we are assuming that there are only 2 switching angles per quarter. Under these conditions, if I want to define a PWM technique, I can just define a PWM technique as a locus of a point on this plane, and this locus begins at V 1 is equal to 0. It can also begin from some V 1 is equal to V minimum if we are not interested in 0, and ends in V 1 is equal to 1. It could be some V 1 is equal to V max, which is less than 1. So, this is, you can define a PWM technique as a locus of a point moving on this plane. It starts from V 1 is equal to 0 contour and finally ends in V 1 is equal to 1 contour or V 1 is equal to V max contour, whatever your V max could be. Alternatively, this is not the only possibility, there are several other possibilities. Let me choose a different color ink here. Okay. Here we go. Now, I say I operate here when I want 0 fundamental voltage. After all, the red point is a good starting point for V 1 is equal to 0, this green point is also a good starting point for fundamental voltage is equal to 0, as we had seen a little earlier. Okay. So, now I want to operate at V 1 is equal to 0, I can choose to operate at this green point here. Now, I want a slightly higher fundamental voltage, something like 0.2 or 0.25 as indicated by the second curve now. I can choose to operate at any point along this curve, but let us say I choose to operate here. Again on the third curve, let us say I choose to operate here. On the fourth curve, let us say I choose to operate here, and I choose to operate here, that is, it becomes square wave now. So, this is again a locus of a point, this is again a locus. This locus again starts at V 1 is equal to 0 and ends at V 1 is equal to 1. This is another PWM technique. This is another PWM technique. So, you can define a PWM technique as a locus of a point moving on the switching angle plane, starting from one point on the curve V 1 is equal to 0 and ending at one point on the curve V 1 is equal to 1. So, that is another way. So, let me take another point here, like here, let us say, shall I use a different colored ink? Yes. So, let us say I use this top. This can also be the one that I have drawn towards the end, can also be a PWM technique. So, this is also because it is a locus of point. So, what all these curves represent certain relationship between alpha 1 and alpha 2. How many independent variables do we have? We have 2 independent variables, alpha 1 and alpha 2, and every one of this curve or every one of this locus gives certain relationship between alpha 1 and alpha 2. So, they are actually reducing the problem to a single variable problem. So, V 1 is now related just to alpha 1 or just to alpha 2 once you have chosen a particular curve. So, it simplifies the problem for you. Now, along this curve, which is good, which is bad, we need to look at the harmonic contents. Already we have seen along this, like for example, let us just call this as A, B and C. These 3 curves is A, B and C. We have already seen A is good as far as 0 voltage is concerned. C is also good as far as 0 voltage is concerned, but B is not so good. We have already seen this now. But this is at 0 voltage, which can be extended, this knowledge can be extended to small amount of fundamental voltages. If this is going to produce a very high amount of harmonic at V 1 is equal to 0, what it means is basically for small values of V 1 like 2% or 5% or 10%, you can still expect the harmonics to be very high, that is with B. If A and C are expected to produce low amount of harmonics at 0, they can be expected to produce low amount of harmonics at small amount of fundamental voltages also. We will be comparing A and C sometime later, but these are just some examples of PWM techniques which I wanted to give now. There could also be other examples. Now, here I have somehow tended to draw, I have had a tendency to draw all of them as straight lines, because straight lines, the equation between alpha 1 and alpha 2 is simplest and the calculations are a lot simpler, right. Now, I do not have to do that. Now, let me say I go in for many more like the same kind of V 1 is equal to constant contours. Let me take, we can now plot many of them fairly quickly, right. Okay. So, let us say we have this. So, let us say we have these contours going like this, just a few of them I have drawn here now. It does not have to be a straight line, it can be anything else also. For example, I can say, I can give one example, maybe I can start here and end up here. I can start here, maybe another example I will indicate with a different color. I can start here and I can end somewhere there else also. All these are PWM techniques. Let me take another example. I can start here and I can go up, come down. Now, what is the problem with this black one? Well, the starting point is not very good. There is another issue. So, let me say the starting point is all right. Let me follow this yellow curve. With this yellow curve, the starting point is okay, but then as you move along this locus, V1 is not monotonically increasing. So, you have multiple values, sometimes V1 goes on increasing here and V1 reaches some local maximum, and after that V1 starts decreasing, and as you move along here and finally V1 which receives some minimum and once again it starts increasing there. So, it is not monotonically increasing. What we would prefer to be is all these curves are all examples of loci along which V1 increases monotonically. If you move from point A and let us call this point as A dash, let us call this other point as A dash, this is B, let us call this B dash, let us call this C, C dash. You move from A to A dash, the fundamental voltage is monotonically increasing, B to B dash or C to C dash, it is monotonically increasing. So, at a for every fundamental voltage you have only one point along the locus that gives you that, whereas if you take this example of the yellow curve here, there are several points, there are multiple points that give you the same fundamental voltage, and this can cause confusions and create troubles when you are implementing them. So, by and large we would want the PWM technique as a locus on the switching plane, starting from V1 is equal to 0 and ending with V1 is equal to, so some point on V1 is equal to 0 and ending at some point on V1 is equal to constant. Not just that, we also want V1 to be increasing monotonically as the point moves from V1 is equal to 0 to V1 is equal to 1. So, that is the other one that we want to say. So, you can look at several examples. Any curve that you draw here is going to be a PWM method, whether it is good or bad, it depends on the harmonic analysis. We can do some harmonic analysis and find out if it is good or bad in what sense there. So, when you say harmonic analysis, we have to look at the harmonic, which harmonics, there are so many of them, there is 5th, there is 7th, there is 11th, the 13th and so on. We are not worried about 3, 9 etc. We are not worried about 3, 9, 15, 21 etc. Why? Because if the pole voltage contains 3, 9, 15 etc., even if the pole voltage contains them, the line to line voltage will not contain these. So, that will not get applied on to the motor. On the other hand, we will be worried about voltages, harmonic orders 5, 7, 11, 13, 17, 19 etc. These are all basically 6k plus or minus 1. You can all these are, you can call them as 6k plus or minus 1, where k is any integer or as a positive integer and you say plus or minus 1. So, 5, 7, 11, 13 etc. These are the harmonics which will cause you trouble now. So, what we have seen is the harmonic voltages see such a harmonic equivalent circuit. So, if you say 5th harmonic, it sees an inductance and the reactance is 5 times the fundamental reactance. If you take 7th harmonic, this reactance is 7 times the fundamental reactance. So, if you take 19th, the 19th harmonic voltage sees 19 times the fundamental reactance. So, as the harmonic order increases, the reactance increases. Therefore, what can you say? It is the lowest order harmonic, n is equal to 5, that is going to see the lowest value of harmonic reactance, and therefore, it could end up producing quite a substantial amount of harmonic current. So, we are looking at 5th harmonic, 7th harmonic, 11th, 19th, all these are problematic for us. So, the one that is arguably most problematic is the 5th harmonic voltage, because for a given amplitude of voltage, 5th harmonic voltage is capable of producing or is going to produce a much higher 5th harmonic current than let us say 7th or 11th or 13th. So, we would target n is equal to 5. We will see, our immediate attempt would be to look at n is equal to 5 and see how good or how bad it is, and we will see, for to achieve the same fundamental voltage, can we reduce 5th harmonic voltage. So, what goes without saying is, if you want to reduce, can you straight away make it 0? So, 5th harmonic voltage is the most problematic voltage, in the sense that for a given amplitude, 5th harmonic voltage will produce greater amount of the greatest amount of harmonic current among all the harmonics such as 5, 7, 11, 13 etc. So, I want to reduce. So, the best thing to do is to totally eliminate this, at least from this point of view. Well, there is 7th, 11th are also going to cause some problems. Eliminating 5th harmonic by itself might not be a very good idea. It can cause to pulsating torque in motor drives, as we will see a little later. But let us say I want to eliminate now fifth harmonic. I am not worried about all that. I just now my intent is to eliminate fifth harmonic. So, I am making that is equal to 0. So, what I want is I want a fundamental voltage V1, and that is given by 1 minus 2 cos alpha 1 plus 2 cos alpha 2. I want it to be equal to some reference voltage or desired voltage. This V star is my desired voltage. It could be 0.25, it can be 0.5, it can be 0.75 or 0.8 or whatever I want. But I want also the fundamental the amplitude of the fifth harmonic to be 0. This is what I want. Can I get this? Yes, I have two equations here and I have two unknowns. So, I can solve for them. I have two equations and two unknowns and I can solve for them. But how do I solve them? These are not linear equations. These are non-linear equations. These are trigonometric equations. These are transcendental equations. So, you can't solve them straight away. So, what we would normally do is we will adopt some numerical iterative procedure. We will adopt some numerical procedure, and I am sure you are all familiar with some numerical methods or the other, such as Newton-Raphson method and Gauss method, and there are several such methods which are taught in the undergraduate course on computational methods or numerical methods in almost all universities. So, I am sure you would have done them as part of this, and there are other courses on NPTEL forum which certainly give you a few things about computational methods. There are lots of computation based courses available, well they can give you a very good feel for these various computational procedures. Now, what I am going to say is all that you need is numerical iterative procedure, though we are not going to get into the details of this here. So, the numerical iterative procedure, you will formulate the equations for solving and you will start with a good initial guess, and with this good initial guess and you go on doing iteration and it will finally go and give you a solution which is very close to the solution, the actual solution, and you will stop somewhere there. Okay. So, what you need to do this numerical solution is you need to start with a good initial guess, or what is called as a starting solution. You need a good starting solution from there. So, to solve these equations you can actually solve from any starting equation. I can just say alpha 1 comma alpha 2 equals 0 degree. That is what comes to my mind, but it may or may not be good. For example, alpha 1 is equal to alpha 2 is equal to 0 is just square wave operation. I may be interested in V star is equal to 0.5, the reference voltage is 0.5, I want to eliminate fifth harmonic voltage. I might be fairly far away from the point where my final solution lies. So, if I have a feel for the problem, if I have a feel for these equations, then I might be in a position to come up with a better initial guess now. Now, if I solve, I will come up with some answer. If I change my initial guess, let us say I can start with an initial guess of alpha 1 is 10 degrees and alpha 2 is 15 degrees, I may end up with some solution. I may start with an initial guess of alpha 1 is 70 degrees and alpha 2 is 75 degrees. If I do that, I may end up with another solution. So, it is possible for you to sometimes get multiple solutions, maybe more than one solution exists now. Sometimes the solution could be unique, that is, no matter what your initial guess is, sometimes it may not converge, whenever it will finally converge to a particular solution only. So, the solution could be unique also, you never know. Then there could be no solution also for some range, for certain values involved. If I can give you an example straight away, take V star is equal to 1 per unit, take V star, I want square wave operation. With square wave operation, V 1 is equal to 1 minus 2 cos alpha 1 plus 2 cos alpha 2 is equal to 1, that is alpha 1 is equal to alpha 2 is what is square wave operation. It is just square wave. In a square wave, a fifth harmonic cannot be eliminated. See, square wave is a square wave, it has a fifth harmonic whose amplitude is 1/5 of the fundamental voltage. So, it is not eliminated, you are not switching at all. So, how can you eliminate the fifth harmonic voltage? So, when V star is equal to 1 or V star is something close to 1 like 0.99 or 0.98, you should expect that there could be no solutions at all to this problem. In fact, there are no solutions to the problem. And in some regions there could be unique solution, in some regions there could be multiple solutions, 2 or maybe 3, I do not know at this point of time. So, one question that I have on my mind is, can I at least say, since the second equation there is nothing there, in the first equation there is V star, and this V star has a complete range, that is 0 to 1, V star 0 less than or equal to V star less than or equal to 1. Is there a range of V star for which I have no solution? Can I identify that range? Is there a range of V star for which I might have a unique solution? Can I identify that range? Is there a range of V star for which there are multiple solutions, say 2? or maybe 3. Can I identify that range? Those are the questions that I have on my mind. So, let us see we can answer those. Before solving all this, you can actually solve these problems. You can put V star is equal to 0.8 or whatever you want, and you can go about solving them. Now, our approach is going to be a little different. We are going to take a graphical approach first now. We are going to take a graphical approach first. We can take a graphical approach because we are only looking at 2 switching angles at this point. So, this will give us some more understanding, some better understanding, better feel of this problem now. So, let us take a look at that. So, what do I mean by graphical approach now? We had earlier drawn V 1 is equal to constant contours, certain constant fundamental voltage contours. Now, I want to focus on fifth harmonic voltage, and I want the fifth harmonic voltage to be 0. So, what I want to do is, I want to identify the set of all points on this alpha 2 versus alpha 1 plane on which V phi is equal to 0. Can I identify the set of all points in this plane and within the region of interest where alpha V phi is equal to 0? That is my question now. How can I do that? Well, we can follow an approach similar to what we did for constant voltage contours. So, what did we do for constant voltage contours? We started off with the equation. We said 1 minus 2 cos alpha 1 plus 2 cos alpha 2 is equal to some 0.6. So, here we are focusing on fifth harmonic. So, we are saying 1 minus 2 cos phi alpha 1 plus 2 cos phi alpha 2, this is your fifth harmonic, right. Of course, it is 1 by 5 factor. When you say V phi is equal to 0, basically 1 minus 2 cos phi alpha 1 plus 2 cos phi alpha 2 is equal to 0. This means fifth harmonic voltage is 0. Now, what you can do is you can plug in a few values of alpha 1 and find out corresponding values of alpha 2. Alternatively, you can plug in certain values of alpha 2 and come up with certain values of alpha 1, fine, we can do that. So, we will get a feel for, we will be able to find out a few points along with, at which fifth is harmonic is 0, and we can connect them and we will get some idea. So, let us start with alpha 1 is equal to 0, it is our friend, 0 is our friend. So, because alpha 1 is equal to 0, cosine of phi alpha 1 or anything is cos 0, cos 0 is 1, we know that very quickly. So, we can solve this now. So, when you say alpha 1 is equal to 0, cos phi alpha 1 is 1. So, 1 minus 2 is minus 1. So, when it goes to the other side, cos phi alpha 2 is equal to 1 by 2, that is 0.5. So, when cos phi alpha 2 is 0.5, what you get is phi alpha 2 is 60 degrees, phi alpha 2 is 60 degrees. If phi alpha 2 is 60 degrees, alpha 2 is 12 degrees, is that right? So, alpha 1 is equal to 0 and alpha 2 is equal to 12 degrees is a solution for V phi is equal to 0. At this point 0 comma 12, you have fifth harmonic is equal to 0. So, shall we go and plot that point on this? What is that point? Alpha 1 is 0 and alpha 2 is equal to 12. So, alpha 1 is equal to 0 and alpha 2 is equal to 12. So, let me use this. Shall I use a different color? I have okay. Let me use a red color here. So, I take this point now. This is my point. V phi is equal to 0. Now, let me look for next point. What could be next point? I am taking alpha 1 is 6. Why do I take alpha 1 is equal to 6? The arguments of the cosine functions are 5 alpha 1. So, 5 times 6 degree is 30 degree. We are very comfortable with cos 30, cos 60 etc., rather than cos 27 or cos 64. So, if it is cos 30, it is comfortable for us, we can readily come up with number, we are familiar with those. So, let me take 5 alpha 1 is 30 is basically alpha 1 is 6. So, let me take alpha 1 is equal to 6 degrees. So, when I say alpha 1 is 6, I have cos 5 alpha 1 is cos 30 and cos 30 is equal to root 3 by 2. So, 2 into root 3 by 2 is simply root 3. So, it is 1 minus root 3. So, it goes to the other side, and so you get, if you plug in alpha 1 is equal to 6 into the equation, you get cos phi alpha 2 is equal to 0.366. You get cos phi alpha 1 is equal to 0.366. So, cos phi alpha 2 is 0.366 mean that phi alpha 2 is 68.5 degree. This is 68.5 degrees and corresponding alpha 2 is 13.7. All right. So, similarly, what I can do is I have 12 degrees. Let me just go and plot that. This is 6 comma 13.7. This is 6 comma 13.7. So, this is something very close to this is 12 and 8. So, this is something like this 6 comma, that is the point. Now, maybe I should not even put a circle around that, that is probably easier. All right. So, when I go to alpha 1 is 12, again 5 times 12 is 60 degree, it is easy for us to come up with. So, I am taking alpha 1 is equal to 12, and if I do that I get cos phi alpha 2 is equal to 0. So, one of the solutions is 5 alpha 2 is 90 and alpha 2 is 18. So, if you go back here, so what I am seeing here is 12 comma 18 is a solution now. So, this is 12 comma 18. So, 12 comma 18 is a solution. Then I go move on, let us say alpha 1 is equal to 18, this has been our approach. We are plugging in some value of alpha 1, finding the corresponding value of alpha 2. If I plug in alpha 1 is 18, cos phi alpha 2 is minus 0.5. If that is there, one of the solutions for phi alpha 2 is 120 degree and alpha 2 is 24 degrees. So, it is 18 comma 24. So, alpha 1 is 18, alpha 2 is 24, this is the point now. Then let me go about increasing, I have been increasing alpha 1 starting from 0, let me go here. So, what I am going to do? I will go to the next point, alpha 1 is 24, alpha 1 is 24. So, corresponding phi alpha 2 is minus 1 and I am getting phi alpha 2 is 180 or alpha 2 is 36. So, alpha 1 is 24 and alpha 2 is 36, alpha 1 is 24 and alpha 2 is 36 is the point here. So, this is the nature of movement here, I hope you can see these red points, this is the nature of the movement as I am going on increasing alpha 1. Let me go increase my alpha 1 further, alpha 1 is 30. So, what do I get? Cos phi alpha 1 is something more than minus 1. In fact, if I substitute any alpha 1 which is greater than 24 degrees like 24.5 or 25, I would end up getting cos phi alpha 2 is beyond minus 1, more negative than minus 1, which is not a permissible value. So, there is no solution. So, what does it mean? It means for alpha 1 is equal to 30, there is no value of alpha 2 which will satisfy the equation V phi is equal to 0. So, along this line alpha 1 is equal to 30, if you go, you can go at any point, you will not find a point at which the fifth harmonic voltage is 0. Whatever you have done is you can join these points, you can join these points and be happy. You can join all these points. You have at least found out a set of points along which or at which the fifth harmonic is equal to 0. Now, the question is, are these the whole set of points or are there more set of points now? That is a very important question now. Have we identified the set of all points in this plane within the region of interest, or have we identified only a few of all possible points? Now, this is something that many students do quite often. So, when I say cos phi alpha 2 is 0.5, phi alpha 2 is 60 is only the principal solution, is only one of the solutions, there are several other solutions. Phi alpha 2 is, when cos phi alpha 2 is 0.5, phi alpha 2 is 60 is one of the solutions. It can also be 360 minus 60, it can also be 360 plus 60 and so on. So, if it is 360 minus 60, what happens? It is 300. So, phi alpha 2 can also be 300. If phi alpha 2 can also be 300, you can say that alpha 2 can also be 60 degrees. Alpha 2 can also be 60 degrees. So, where is that 60 degrees here? Let me come here. Alpha 1 is 0 and alpha 2 is 60 is another point here. Similarly, you go to the next one. You say alpha 1 is 60, cos phi alpha 2 is 0.366. So, phi alpha 2 is 68.5 is only one of the solutions. Phi alpha 2 is also equal to 360 minus 68.5, 360 plus 68.5 and so on. So, here also you have 12, 60 is 360 minus 60 in the earlier case, it is also 360 plus 60 which is 420. So, 420 by 5 is 70 degrees. So, not just that, I also had 72 degrees here. So, 72 degrees is like this, 72 degrees is like this now. So, let us just consider one other set of solution. If it is 360 minus 68.5, your alpha 2 is going to be something different. 360 minus 68.5 is something like 291.5. 291.5 divided by 5 is something like 58 or so. So, what you are going to get is like this. What you are going to get is like this now. Similarly, if you consider the second solution, right, 360 minus whatever, then you will find that these are the points you will get, these are the points you will get. So, if I come here alpha 1 is equal to 18 for example, cos phi alpha 2, phi alpha 2 is 120 or it can also be 240. So, 240 by 8 is 42 degrees. So, 18 comma 48 is another solution. This is 18, this is 36, 42, 48 is another solution now. So, what I will have is I can also do this like that. So, this curve is in fact something like this. This gives a fuller picture of what we want, but not full yet. I mean it is not complete yet. Why? We have considered only one other set of solutions, that is cos phi alpha 2, we have come up with phi alpha 2 is its principal solution or 360 minus the principal solution. It can also be 360 plus that. So, if you do that, you will start getting points here, you will start getting a few points like this, you will get a curve going up like that. So, what do these mean? Various solutions are there. There are several solutions for a particular value of alpha 1, you get several solutions of alpha 2. So, you go about getting many of those solutions now. So, let us say you have drawn these now. So, let us now get a little wiser, the set of all points, let us now get a little wiser. It is all right to calculate points like this and we have come up with some contours now. So, what we can do is you can come up with a complete thing of all the 0 fifth harmonic voltage now. So, before that we can also see how the slope of V phi is equal to 0 varies, how V phi is equal to 0 varies. So, V phi is equal to 0 has this equation 1 minus 2 cos 5 alpha 1 plus 2 cos 5 alpha 2 is equal to 0. This is the equation V phi is equal to 0. If you want to find out the slope, differentiate both sides with respect to alpha 1. So, what we are going to get is something like 10 times sine of 5 alpha 1 minus 10 times of sine 5 alpha 2 multiplied by d alpha 2 upon d alpha 1 is equal to 0. So, in effect what you get is d alpha 2 upon d alpha 1 is basically sine of 5 alpha 1 by sine of 5 alpha 2. Earlier for V 1 is equal to constant curves, we had the slope to be sine alpha 1 by sine alpha 2. Here V phi is equal to 0, we are interested not in V phi is equal to constant, we are interested in V phi is equal to 0. Why? Because we want to eliminate the fifth harmonic voltage. So, along this again we find sine phi 1 by sine phi alpha 1 by sine phi alpha 2, this is what we are finding now. So, if you consider the line alpha 1 is equal to 0 degree, you will have slope is equal to 0, because sine phi alpha 1 is sine 0. So, slope will be 0. And when is the slope infinity? Slope can sometimes be infinity, slope can be infinity, that basically implies sine of 5 alpha 2 is 0, whenever sine of 5 alpha 2 is 0. When can 5 alpha 2 be 0? Sine 5 alpha 2 can be 0 when 5 alpha 2 is equal to, let us say 0 or equal to 180 degrees or 360 degrees or 540 degrees and so on. So, correspondingly the values of alpha could be 0, 180 by 5 is 36, 360 by 5 is 72 and so on. This is 108 and so on. So, for all these values of alpha 2 you have infinite slope. So, you come back here, if you go to the old curve for at alpha 2 is equal to 36 degrees, at alpha 2 is equal to 36 degrees, let me do it with a different color here. This is alpha 2 is equal to 36 degrees, it is along this line we had a curve there. So, now what we can do is we are a little wiser, we know what the points are and we know where the slopes are infinity and where the slopes are 0 now. So, if you plug in alpha 2 is equal to 36 degrees into your V phi is equal to 0, you will get alpha 1 is equal to 24 degrees. Alpha 2 is 36, gives alpha 1 is equal to 24. So, if you put alpha 1, then you will get alpha 1 is equal to 24 degrees, that is this point. So, let us now do it. Earlier we were just trying to explore to find these points. So, now if you do it comfortably, what you can do is you can find out all the extreme points, that is 6, 12. So, these are the extreme points which can be easily found out. 6 or sorry, it has to be 12 at 60. So, let me erase this off. So, you can go about drawing them from here to here, you will have a curve, and this is at 36 and 24. So, the nature of the curve is going to be something like this. This is the nature of the curve. You can have yet another curve. This curve actually goes on both sides. This actually goes on both sides. We are not interested in the left hand side. So, now what you can do is you can shift this curve by 72 degrees. Why 72 degrees? If you shift it by 72 degrees, it is 360 degrees for the fifth harmonic. So, you can shift it to the right or to the left or top or anything, and you will get these curves again. So, you can get lots of V phi is equal to 0, and you can look at all those curves within your region of interest. So, that is how you can get lot of your fifth harmonic voltages. So, it will not be one curve. So, this if you shift it up, you are going to get another curve like this. You are going to get another curve like this. If you shift it this side, there could be yet another curve, but that may not be useful for you. But if this curve is shifted up, you will get yet another curve which is going something like this. So, there are several such curves which will be of interest to you, and this is your V 1 is equal to 0. So, V 1 is equal to 0. So, within this region you have number of solutions we will discuss. So, this part can give you some fifth harmonic solution, and this curve can give another fifth harmonic, some other fifth harmonic solution. So, we will discuss these various solutions in detail in our next lecture. So, thank you very much for being with me, and I hope you enjoyed this lecture, and I hope you will have continued interest to follow the next lecture. Thank you very much.